of influenza vaccines for use in the Southern Hemisphere 2025. My name is Wenqing Zhang. I'm heading the WHO's Global Influenza Program. The opening remarks for this information will be given by Dr. Mike Ryan, the Deputy Director General of WHO and the Executive Director of the WHO Emergency Program, of course, remotely, and of course, in video, because our meeting today is taking place in Melbourne, Australia. So let's show the video now from Dr. Mike Ryan.
Dear colleagues and friends, good morning to you all. It's a pleasure to join you remotely today. For the past number of years, I've joined the biannual vaccine composition consultations either remotely or in person. These meetings are very important as influenza has always been a priority for you and for WHO. Let me start by thanking you. For more than 70 years, both GISRIS and the vaccine manufacturers have provided continued and consistent support in influenza surveillance, risk assessment, preparedness, and response. Influenza was recognized as a global public health priority in 1947. Since 1952, the Global Influenza Surveillance and Response System, GISRIS, has proved to be the bedrock of influenza surveillance, preparedness, and response. GISRIS is a vital asset for global health. It has grown from a handful of countries to over 160 countries worldwide today, and it keeps on growing year on year and acts as a global alert mechanism. When we have a respiratory virus that poses a pandemic threat, every second counts. Every year, as many as 1 billion people are infected with influenza, with as many as 5 million people suffering from severe disease and 650,000 people dying. This is a tremendous burden on society. More can and should be done to reduce this burden. Furthermore, we have seen the unprecedented global spread of avian influenza H5 viruses in animals, which has caused huge economic disruption and loss globally. Worryingly, it raises the prospect and real threat of an influenza pandemic. The success of GISRIS is thanks to the enormous support of hosting countries, international partners, including all of you. Beyond influenza surveillance, preparedness, and response, GISRIS has been and will continue to be leveraged for other respiratory viruses, including RSV, SARS-CoV-2, and in some parts of the world, MERS-CoV. Expanded GISRIS or eGISRIS is playing an important role for other respiratory viruses. Vaccine is the primary intervention to reduce morbidity and mortality associated with influenza. Seasonal influenza vaccination averts severe disease outcomes from influenza and saves lives. Moreover, capacity built through the seasonal influenza cycle strengthens pandemic influenza vaccine response capability, and this is vital for the future. All of this is possible only because long-standing public-private partnership based on collaboration via GISRIS. We look forward to deepening joint efforts to constantly improve influenza prevention and control. I thank you for your dedication, for your support, and wish you another successful round of influenza vaccine cycle for the Southern Hemisphere in 2025. Thank you.
So actually, Mike has opened the WHO information meeting in the past many years, twice a year. That also shows the importance of influenza in the WHO's public health agenda. Without further ado, let's move to the next agenda item, is the selection of chair. So as many of you know that the chair of this information meeting and the roundtable discussion is always chaired by an advisor. And this time, we've invited Dr. Ziping Yi from CBER FDA to be the chair for the information meeting today. Let me just ask the floor if there's any comments, any concerns or objections against this proposal. No? Hearing none. Okay, so Dr. Ziping Yi will be the chair of this information meeting, and I just pass over to him.
Thank you, Wenqing. I'm honored to be a chair for today. I think in the last few months, this group, WHO, CCs, ARLs, and National Influenza Centers have been analyzed the viruses activities in human and in animals. And this week we gathered in this beautiful city. I'm impressed by how beautiful, how clean that city is. So you should be proud you're living in this city. So in this week, we further summarized, analyzed antigenic and genetic information over the viruses. And also we include vaccine effectiveness, human serologies, and modeling. I think so we use those information to select the viruses that could be used for next season. And also, as Chris mentioned, that vaccine candidate is viruses is so critical because that is the critical element to deliver the vaccine to the market. So without further delay, I think the first maybe is good to introduce the advisors from here. We start from my left hand, Hideki.
Good morning, everybody. This is Hideki Hasegawa from the WCC Tokyo, Japan at NIAID.
Good morning, everyone. My name is Otmar Engelhardt. I'm from the ERL at the MHRA in the UK.
Good morning, everyone. Ian Baum, the local boy from Melbourne.
Good morning. You look slightly better. Good morning, everyone. I'm Nicola Lewis. I'm the director of the WHOCC in London.
Good morning. I'm Rebecca Condor. I'm the interim director at the WHO Collaborating Center at CDC Atlanta.
Good morning, everyone. This is Dai Wang from WHOCC Beijing, China.
Good morning, everyone. This is Vasily Marchenko, director of WHOCC in Koltsovo, Russian Federation.
And lastly, I'm Pearl Bamford from the Therapeutics Good Administration here in Canberra as the NARL. Thank you.
Thank you, everyone, for the introduction yourself. We will start with the H1N1, H3N2 B viruses and zoonotic influenza viruses to to present the data and why we choose what we choose. Then after that, Wen-Jing will announce the selection, which one we choose. Probably that's the most important for everybody to sit right here. Then later on, to deliver vaccine on the market, we do need to have adequate vaccine candidate viruses, reagents, and that have to be it will be presented. Then first we introduce Nicola Lewis from WHOCC UK.
Good morning, all. Thanks, Chair, for that introduction. I'm going to present a very brief summary of global influenza activity, first of all, before I move on to the summary of the H1N1 PDM09s. Let's do it. It's all right. Okay, so this is a graph that shows the number of specimens processed by GISRIS by week for the past 4 years. And really focusing in on the purple line shows you the number of specimens that we've been processing throughout 2024. And it really mirrors the trajectory of these samples that have been processed through 2023. So post-pandemic, we've really been seeing the same rates of processing by the GISRIS network as a whole through this period. As we know, influenza activity has significantly picked up in the post-pandemic era, and you can see here the global circulation of influenza viruses through 2022, 2023, and 2024. What we see between 2023 and 2024 is really a similar kind of distribution. We also see probably a slight broadening of the global circulation activity through 2024, whereas in 2023 we saw a little bit more of a bimodal distribution to the circulation. And here's a map that illustrates our global reach. So this map shows the countries, areas and territories that shared viruses with the WHO-CCs in this period. And really, we have a pretty comprehensive reach in many of our geographic regions. And it's really a great credit to GISRIS that we have this huge collaborative effort across the globe that allows us to underpin the vaccine recommendation. When we look at sequencing data, these are the numbers for influenza viruses that have been genetically characterized by the collaborating centers since February 2024. And you can see that we've had significant numbers of H1N1 PDM09s, H3N2 viruses and B Victoria viruses, and still, as per post-March 2020, no detections of B Yamagata viruses. We also antigenically characterize these viruses, and here's a plot that shows the total viruses antigenically characterized in the past 4 seasons. And really focusing in on the red bars here, we have been characterizing phenotypically significant numbers of H1N1 PDM09s, H3s, and indeed B viruses, in some cases more than in the previous season, particularly for the H3s. So that's a brief update on the global circulation of influenza. I'm now going to move on to discuss the AH1N1 PDM09 viruses for this reporting period from February through to August 2024. And again, here's a plot of the number of AH1N1 PDM09 viruses detected by GISRIS. A little bit of a different trajectory than we've seen perhaps in 2023, where we saw a large spike in the early part of 2023, followed by a dip and then a resurgence. We see a different trajectory in 2024, where we didn't see so many viruses in what would be more traditionally the Northern Hemisphere season for the AH1N1 PDM09s, but they have continued with a longer tail through to the current months at this juncture. When we look at influenza A H1N1 PDM09 activity globally, you can see here that we've had significant positivity rates, particularly in the European region, but also more broadly in parts of South America and in North America and in parts of Southern Africa. Moving on to the clade distribution. So along with circulation, we've also seen expanded genetic diversity. And this has really been a story that we've told you probably for the H1s and for the H3s over the past few reporting cycles. So this is the global clade distribution for the H1N1 PDM09s from the 1st of September 2023 through to the 31st of January. And if you note the legend in the top right-hand corner, this is an illustration of the standing genetic diversity we had in this time frame. If I click on to what we now have, you can see that we have expanded genetic diversity in the H1N1 PDM09s, and the distribution of the genetic groups that circulate worldwide really depends on which member state and which region you're in. So we can see here that we've probably had a predominance of the C1.9s in particular in Europe, a rather more mixed picture in the Americas, perhaps with a more predominance of the D and the D derivative lineages. And again, if we move over towards Asia and sub-Saharan Africa, again, a little bit more of a mixed picture with some predominance of the C1.9s, but also co-circulation of some of the D derivative and indeed the C.1 groups of viruses. So this is quite a complex picture genetically for us to try to keep abreast of. We also antigenically characterize these viruses to understand what the phenotype looks like in relation to the genotype. And so here you can see a plot of how many viruses the collaborating centers have antigenically characterized over this period. What I'm now going to do is show you the latest genetic information that we had for these viruses. And so this is a phylogenetic tree kindly generated by the University of Cambridge, and my thanks to both Derek Smith and to Sarah James for this work. And on the left-hand side, you can see the phylogeny. And on each of the nodes, you can see the amino acid substitutions associated with the divergence at particular points in the phylogenetic tree. You can then see a plot in the middle with tick bars down it, which illustrates where those particular viruses were located spatially around the world, where they circulated. And the key on the left-hand side tells you the region from which they came. So if we look a little bit more closely at this plot, and I'm just going to put up a laser pointer here to illustrate a little bit more clearly, you can see what we've had here. As we saw in the previous geographic distribution plot, we have found that there's been a predominance and more recent circulation of the D groups of viruses and the derivatives, particularly in the Americas. And you can see this indicated by the blue tick bars in this part of the plot. Whereas further down here, as we move more east, we've seen a predominance, particularly the C1.9 viruses. But what does this mean antigenically? So on the left, we're taking the same phylogenetic tree and the same distribution geospatially. And on the right-hand side, we have antigenic maps. Antigenic cartography is a way to quantify the HI assay titers from our phenotypic data. And I'm just going to take a moment to walk through antigenic maps and how to read them. So all the viruses in an antigenic map are represented by these little coloured circles. And the current vaccine recommendations are represented by these larger circles. And you can see in the legend that we've named them. So this pink dot is Victoria 489722 egg representative, and Wisconsin 672022 is the cell representative in blue. And if you look very closely, you can see that there are some very small squares. These grey squares represent the ferret antisera that we use to characterize the viruses in the HI assay. And what antigenic cartography does is quantify the interrelationships between the antisera and the viruses. So we take the HI data and we turn it into an antigenic map. There's no directionality to an antigenic map. You can read it any which way you like, upside down, but it's the interrelationships between those points, the antigenic distances that matter. And how do we represent antigenic distance? Well, there's a grid behind the antigenic map you can see here. And each one of these squares represents a twofold difference in the HI assay, or one antigenic unit. So if we were thinking about a fourfold difference in antigenic properties, we'd expect to have two antigenic units or two squares between these viruses. Likewise, if we were thinking about an eightfold difference, we'd expect to have three antigenic units or three squares between the viruses. So if we move through these panels in turn, we've had expanded genetic diversity, but you can really see that these points, these latest detection of viruses, latest characterized viruses, are still quite closely associated with the previous recommended strains. And you can see that because there's very little antigenic difference between the colored spots and the vaccine strains that you see in the plots. We can interpolate some serum circles over this, and really these visually show us the viruses are falling within an eightfold of the vaccine antiserum. So you can see despite this expanding genetic diversity, what we see with the H1PDM09 viruses, they're really quite closely associated still with the current vaccine recommendations. We can summarize this antigenic analysis in different ways. So here we have the antisera to the Southern Hemisphere 2024 vaccine virus antigens, the A Wisconsin 672022 cell-like, and the A Victoria 48972022 egg-like. And you can see for all collaborating centers, good recognition for the currently circulating strains by the vaccine serum, whether we look at the egg or the cell. This is mirrored in our analysis using post-vaccination sera. I'd like to thank the WHO-CC in Atlanta for these data. And really here we're looking at the recognition for these currently circulating strains in a number of different panels for a number of different genetic groups for the A Wisconsin 672022 cell-like representative and also the A Victoria 48972022 egg representative. And you can see here really, particularly for the cell, which is usual, good recognition for the geometric mean titer ratios in these particular serum panels. So I'm going to move on briefly to summarize our findings on the antiviral susceptibility results. We assess different groups of antiviral susceptibility antiviral options, and the first is the neuraminidase inhibitors. And in this reporting period, we've analysed over 3,000 H1N1 PDM09 virus clinical samples and isolates. We do this in a couple of different ways. One is by looking at the genetics, and in some cases following up with phenotypic analysis. Of these 3,300 specimens examined, 63 showed evidence of reduced susceptibility to NAIs. And you can read there the substitutions that were identified. We then go on to phenotypically test these viruses. And of the 63 that were phenotypically tested, 55 of these showed reduced or highly reduced inhibition by NAIs. We do similar work for the endonuclease inhibitors, and here of 2,612 AH1N1 PDM09 viruses, again examined either by genetic and or phenotypic analysis. One had a PA substitution of I38V and one had a PA substitution of I38N. And the one with the I38N showed evidence of reduced susceptibility to the endonuclease inhibitor baloxavir marbacil. Finally, to wrap up, summary for the influenza A H1N1 PDM09 viruses. I hope I've shown you from the phylogenetics that we have continued global circulation, and these viruses have genetically diversified during this reporting period. The hemagglutinin genes still remain within the large 5A.2 clade, with diversity continuing to emerge into two different subclades, the 5A2As and the 5A2A1s. And then these are diversified further into subclades, with the C1.9s predominating in most regions, except in North America and some countries in South and Central America, where the 5A2A1 group predominated. Moving on to the phenotypic analysis. Post-infection ferret antisera raised against the Southern Hemisphere 2024 and the Northern Hemisphere 2024-2025 AH1N1 PDM09 vaccine components. So those are the cell culture propagated, A Wisconsin 67 2022, and the egg propagated, A Victoria 4897 2022, from the 5A2A1 subclade, recognized the 5A2A and the 5A2A1 virus as well. And when we look at post-vaccination GMTs, these were not significantly reduced for the most recently circulating strains of AH1 PDM09 when compared with the A Wisconsin 67 2022. So that wraps up the summary of our analysis for the H1N1 PDM09 viruses. And I think I'm going to pass over to Rebecca Condor to move on to the H.
Okay, good morning, everyone. It's my pleasure to talk about the virus characterization and circulation of the AH3N2 viruses. So our reporting period covers February to August of 2024. And as Nicholas showed, looking at the Gistris detections, H3N2 was detected throughout the reporting period. We can see at the end of 2023, a very large peak in H3N2 detections. And this is followed through to the purple representing the 2024 detections. I'm not sure if the pointer works. Does that work? Okay, thank you. That's helpful. Okay, great. And so we see an increase or detections in the beginning of 2024, continuing throughout into the Southern Hemisphere activity this season. So H3N2s seen globally and throughout the Southern Hemisphere reporting period. When we look at a map at the reporting period from February to August, several regions had a significant proportion of their influenza viruses subtyped as H3N2. Of note, the Americas, Central and South America had quite a robust amount of H3N2 activity, as well as parts of Europe, Africa, West Asia, Southeast Asia, East Asia, and Oceania. So quite a lot of H3N2 viruses circulating. Shown previously by Nicola, this is our large phylogenetic HA tree of the H3N2 hemagglutinin provided by the University of Cambridge. What we saw going into February's VCM was the spread of a single clade, the 2A3A1s, throughout the world. And the further diversification in the HA gene broke these into subclades J1 through J4, labeled here on the tree. And at the February VCM, we saw co-circulation, but regional differences in which a J subclade circulated. So we continued to see J.1 and J.2 viruses significantly during this reporting period. And as you can see by the distribution and total number of tick marks under the J.2 subclade, quite a number of J.2 subclades continued to circulate from February to August. And as mentioned by Nicola, the location of the tick, the color of the tick marks demarcates the location. And so you can see that J2 circulated globally, so throughout the world. And by looking at the color, you can see there's co-localization in some regions for particular genetic changes in the J.2s. But in general, you see a much broader increase in the number of J.2s detected since February compared to the other subclades that were previously identified. And I wanted to highlight a couple of substitutions in the hemagglutinin shared in the viruses that have the HA gene expressing the subclade J.2. So this is a picture of the monomer of the hemagglutinin. And what we can look at is different antigenic sites within the molecule that have previously known to affect the ability of antibodies to bind when we see changes in them. So in green, we have the antigenic site A. In a light peach, antigenic site B, in a purple, antigenic site C, and in cyan, antigenic site D, and yellow, antigenic site E. And so the two particular changes that we have for subclade J2 are positions 276 and 122, with 122 actually encoding a change in a putative glycosylation site to a loss of a putative glycosylation site, potentially opening up this part of the molecule for antibodies to recognize. So these were the two main changes that were responsible for and found in the majority of viruses that circulated from February until now. Okay, so now that we all have a little bit of background of the protein that is out there, let's kind of take a look at the J.2s themselves and what further diversity we can see in these viruses. These maps show the changeover in clade diversities that circulated from the previous reporting period, so September to January. And as I mentioned, we had a lot of different J subclades circulating. So these are in different shades of green. And of note, you can see that J.1, which is in a more brighter green, was found globally and in some places actually predominated during this time period. We also see that Africa had a good mixture of genetic diversity of the hemagglutinins, including those in pink, which represent viruses in the 2A3 clade and the subclade G.1.3.1. But we can just see the beginning of an increase of the J.2s during this reporting period. And as we switch from February to August, you'll notice the increase in the dark green representative of the J.2 increase in detections globally. And in the regions that had significant activity, the majority of those were due to J.2 viruses. And even in parts of Africa where I mentioned there were still detections of other J clades and the 2A3 subclades, you can now also see introduction and detection of J.2 in these regions as well. So we can see J.2 was responsible for the majority of H3N2s in the countries and regions I mentioned with increased H3 activity, including parts of Asia, Southeast Asia, and Oceania. Overall, this shows the number of H3N2 viruses that have phenotypic testing through our antigenic assays over the last 4 reporting periods. So all collaborating centers had significant H3N2 viruses to analyze, and you can see the spread and change during the reporting period for each of the collaborating centers. This summarizes the results of the hemagglutinin inhibition assays using ferret antisera raised to the cell and the egg vaccine viruses. So the vaccine virus, Massachusetts 18 2022-like, represents the cell viruses from the 2A3A1 clade. And Thailand 8-like viruses grown in eggs represent the egg-based vaccine viruses. So the same clade. As of note, you can see that all centers showed reductions to the Massachusetts cell-like ferret antisera, although in different proportions. And this reflects some of the genetic diversity of the viruses tested in each laboratory. But an increasing number of viruses were found to have reduced HI inhibition greater than 8-fold during this reporting period to both the ferret antisera raised to Massachusetts 18 and Thailand 8 egg. So the HI assay looks at some binding properties of the virus and the antibodies to prevent agglutination, but we also analyze the H3N2 viruses in virus neutralization assays, trying to understand the antibody titers that the naive ferrets produce post-infection and whether or not they inhibit the infection of the virus in the cell. The results for H3N2 viruses using virus neutralization saw a little bit different pattern. Smaller numbers of viruses showed greater than 8-fold reduction in the virus neutralization assays when looking at post-infection ferret antisera raised to Massachusetts 18, but larger proportions show reductions with the ferret antisera raised to the egg Thailand 8 virus. So one of the important things that we want to look at once we have a phenotypic result is going back to the phylogenetic tree and understanding the molecular determinants of our reductions seen in our antigenic assays. So at CDC, we can see that this is the phylogenetic tree of the H3N2. And what we do is bin the viruses into different subclades, as mentioned. And then each virus that has a test result, we include the result of the test as a bar that is equal to the location of where it is in the phylogenetic tree. And so we're looking for co-localization of viruses with reduced reactivity to understand which of the molecular changes we can see in the sequence could be potentially responsible for this change in phenotype. What we've noticed with the H3N2 viruses, and this is the HI assay with ferret antisera to Massachusetts 18 cell, is that we saw a good coverage of the majority of viruses that were very close to the base of the 2A3 and the J1 and J2 genetic tree. But once we started to see additional accumulations of mutations throughout the tree, the reactivity started to decrease for H3N2s. And looking at the different changes in the hemagglutinin, we were seeing convergent evolution at several sites. One in particular is position S145N, which I've put here on the molecule on top of the J.2. And here you can see it's in antigenic site A, very near the receptor binding pocket. And we saw this particular substitution actually appear on several different subclades throughout the tree. And it corresponded with reduces in the reactivity of our ferret antisera. And then when we look at reactivity that's quite high fold reductions, represented by the greater than 8-fold bar and colored purple here, here's where we're looking for additional substitutions upon the different subclades that conferred really a reduced or lack of reactivity with our ferret antisera. Particularly, there was 2 sites that we saw most often that were responsible for this low reactivity. And that included a change of position 189 here at the top of the site B, which we've known in several different historic changes in antigenic drift being responsible for differences in the H3. Sometimes this happens with and without position 145. And then we also saw several subclades that had a change of position 158K, also in site B, but a little bit further back from the receptor binding pocket. So these were very clearly low reactors in all of our assays. And so the next question is, are these particular subclades that have these changes continuing to circulate and increasing in proportion? And luckily for these particular two substitutions that I mentioned, they represent very rare subclades in circulation. However, the viruses with changes at 145, as I mentioned, are continuing to be seen throughout many subclades over this period. When we look at an HI assay, where we have Vera-Anasera post-infection to the vaccine viruses, we started to expand the panels to include representatives of the J.1, J.2 clades and the additional changes that they have. So specifically, we're looking to see whether or not the reactivity patterns for Massachusetts and Thailand can be affected by specific subclade changes or additional changes within that subclade. And we can walk through this HI test kindly provided by the WHOCC in London. And we can see that Massachusetts, homologous titer of 640, starts to see reductions in the J.2s when additional substitutions of 145 are seen. Also picks up lots of reductions or high levels of reduction for viruses that have the N158K substitution. And if we look, there are some J.2 viruses that are recognized fairly well. But again, as we look at different representatives with accumulative mutations at 145 and 189, we start to see a loss of reactivity. And the same pattern can be seen with the Vera-Anasera raised to the egg-based Thailand 8. Now, looking at our reference viruses for the J1s and J2s, one of the questions we're asking is how broadly cross-reactive will the Vera-Anasera be for these new reference viruses? We have a reference virus to the J1, which is also starting to see reductions in the position, the J2s with the 145, the 158, and the 189. And when we make Vera-Anasera to a J2 representative, Croatia 10136RB 2023, here we see improved recognition in the genetic diversity of the J.2s, including those with changes at position 145, which it itself has. However, we are starting to still see some reductions in viruses to the 158 and the 189, but not to the magnitude that we see with the Vera-Anasera to Massachusetts 18. Similarly, the profile of the Vera-Anasera to the egg-grown Croatia has a similar pattern as just described. And as of note, we also are looking at the J.2 viruses with those significant antigenic changes and to see how well they cross-react with other viruses without those changes. And so this shows our Slovenia reference virus raised to viruses with the 158K substitution. It has a good high homologous titer, but shows great reductions throughout all of the viruses that are circulating. So it doesn't represent a protein that would give broad reactivity. So the question is, are all WHO collaborating centers seeing this particular change in the J.2s? And so we look at the use of the antigenic cartography to look at the location of the different subclades. So just to orientate everybody, as Nicola mentioned, this is an example of the HI assays from the CC in London and Melbourne. And the viruses are color-coded by the J subclade. Viruses in dark green are the 2A, 3A viruses that we, as I mentioned, still circulated in parts of Africa. And then the J viruses in turquoise represent the vaccine viruses that were for Massachusetts 18 and Thailand 8. And then in purple and pink, we have the different subclades of the J. The J.1s in the darker purple, J.2s in pink, J.3s in a light purple, and J.4s in probably the lightest purple or lilac color. One thing to note is that we can look at the 2A, 3A ones and the J.1s and J.3s, and they all cluster together in the antigenic map. showing antigenic relatedness to each other and to the cell reference virus Massachusetts 18 like. But if we look at the trends for the J2s, we can see a shift in the location of the viruses, not only a little bit north in this map of the Massachusetts 18, but a larger spread as well out. And the same spread we can see in the data from the Melbourne HI. At the very fringes, you can see viruses greater than 8-fold in the J.2s are represented by the viruses with the particular substitutions I mentioned, such as 158 and 189. And in particular of note, that light lilac shown in the London CC data represents the J.4s, which themselves have a subclade with an additional change of K189R. Showing being most antigenically distinct from the representative ferret antisera. I'm now going to take the London HI map and show you the serum circle for the current vaccine virus and also some of the updated reference viruses. So this map now has a serum circle showing where the viruses that respond within 8-fold of the homologous titer for Massachusetts lie. And what we can see is a concentration of the J.2s at the very edge of the reactivity of the sera raised to Massachusetts 18, and quite a few following outside, as well as those from the J.4 I mentioned with the 189 change. If we look at our reference virus ferret antisera to Croatia, it belongs right in the middle of the majority of the J.2s and shows great increased coverage in reactivity of the J.2s, although we are still seeing some viruses with particular changes at 158 and 189 that have greater than 8-fold reduction, and similar for those in the J.4s with that 189 substitution. So this is all the data I'm showing you with a naive post-infection ferret antisera. And so the next question that we wanted to ask is looking at panels of individuals vaccinated with this Southern Hemisphere season's Massachusetts 18-like and Thailand 8-like vaccines, how well did their titers to the vaccines react and recognize the new diversity that we're seeing across the J and the J.2 viruses. And so we have panels from Australia, Peru, and Hong Kong that include both the adult that received the cell-based vaccine, as well as adults that received egg-based vaccine, and two panels that received the egg-based vaccine in the elderly, either an adjuvanted or regular quadrivalent egg-based vaccine. We saw robust titers to the vaccine reference viruses in the subset that we chose specifically to look at how well those antibodies then recognize the circulating viruses. And what I've shown here are the different subclades. Within each subclade, the viruses that were tested were ones that were recognized to have reductions, either small reductions or great reductions in our phenotypic assays. And so what we see is that viruses with additional substitutions within each of the clades, both the J.1 and the J.2 and the J.4, showed significant reductions in GMT titers compared to the vaccine viruses. And this was especially true when there were additional substitutions within each of these subclades, including positions 145, 145 and 189 together, and 158. So human sera, which has a little bit different history than our ferrets, is showing significant reductions in titers compared to the vaccine viruses. So in summary, H3N2 viruses predominated in some countries, areas, and territories, and there was significant H3N2 activity observed in Central and South America, North and Western Africa, Southeast Asia, and Oceania. Looking at the phylogenetics, although the clades used to be a little bit easy to digest, we did see co-circulation of 2A, 3A, and 2A, 3A1 clades. But as we tend to break these clades apart and look for changes in the HA as well as the proportion change over time. And so looking at the J.1.J.4 HA sequences, we're seeing further diversification. And then looking at the proportion changes, we see a predominance of J.2 in most regions. But as I mentioned, there were parts of Asia, Africa, and South America that did also see significant J.1 viruses circulating. And still seeing small numbers of the J4 and the 2A3 viruses in some countries in Africa. So as we look at the HA gene of the clade 2A through A1s, as noted, we're seeing several substitutions emerging across different subclades, showing convergent evolution. Of note, the positions 145, 158, and 189. And looking at that in the lens of the ferret anasera and the phenotypic assays, while most viruses expressing the J.1 and the J.2 HA genes were recognized well by the Massachusetts 18 and Thailand 8 ferret anasera, that ferret anasera has begun to show reduced to poor recognition with viruses with additional changes within the J.2. Of note, the 145, and then the poor recognition of viruses with the 158 and the 189. And also of note, as I mentioned, the J.4 subclade still in circulation that also shares that K189 substitution. When we look at improved coverage of these viruses, we see that a reference viruses to subclade J.2 that has the 145 substitution, represented by District of Columbia 27, 2023, and Croatia 10136 RV 2023, recognize the majority of circulating viruses as well. Our human serology studies using serum panels from individuals vaccinated with 2A3A1-like viruses. In this result, we showed post-vaccination GMTs to many of the recent H3N2 viruses from the J.1 and J.2 subclades, with those additional substitutions showing significant reductions in most serum panels. Looking at our antiviral susceptibility analysis, again, looking at both the genotypic or phenotypic evidence, we analyzed over 3,480 H3N2 viruses, and one showed evidence of reduced inhibition to neuraminidase inhibitors. Looking at susceptibility to endonuclease inhibitor, baloxavir marboxyl, we analyzed 3,269 H3N2 viruses, and 11 showed evidence of reduced susceptibility. Thank you. I'm now going to turn it over to Ian Barr to go through the Influenza B viruses.
Okay, thank you, Becky. I think I've got the easy job after that presentation. What do I have to do here? Witching.
Just
Okay, got to do something. It's always difficult.
Here, which one is yours? 4, right? No, 3.
3. Yep. Okay, so I just go. Right, okay. Thank you, Wenqing. That's why we give her the top job. I'd just like to thank CSL for hosting the meeting today. Otherwise, it would have been over at the Doherty and we would have to employ security staff and my staff would have to come in on a public holiday. So instead, that's going to fall to CSL. So thanks very much for hosting this meeting and for all the WHO crew for making the long trip to Melbourne. We're only here because it's options, obviously, next week. So Influenza B is a sort of forgotten child for influenza. Everybody focuses on influenza A, but influenza B does have an impact on human health. Usually 25 to 30% of the viruses each year are influenza B viruses. However, we are having a bit of a quiet year with influenza B viruses in this current period. You can see here on the graph here that the 2024 shown in that purple line there is relatively quiet so far this year compared to the green line shown in 2023 where we had much more activity. But B will be back, mark my words. So we know that influenza B comes in two flavors, two varieties, influenza B Yamagata lineage and influenza B Victoria lineage. Fortunately, the GISRIS program has killed the B Yamagata lineage with a little bit of help from COVID-19. So we've seen very little or no circulation of detectable confirmed B Yamagata since March 2020, and that's shown in this graph here. We don't type every virus that comes through the GISRIS network, but we do type a reasonable proportion. And you can see there that the green is the B Victoria lineage going up and down, and the blue is the B Yamagata lineage, which is flatlined after 2020. So this just reminds you that the proportions of influenza B compared to the A viruses that we've seen in this period. So around about 30% of the viruses typed being influenza B. When we look at the lineages, as I've mentioned here, the ones which have been typed, which is about a third of all of the viruses which come in as influenza B, have been typed as B Victoria, and zero, an absolute zero B Yamagata viruses have been detected. So here is a heat map of influenza B activity, and as I've already briefed you, that it's been relatively quiet so far in this period, with the exception of Japan. You can see on that map being highlighted in red, but activity in many other parts of the world as well. So just to reiterate that, in case you didn't get my message, there has been no B Yamagata virus detected. So that's the last word I'm going to say on B Yamagata. Okay, so now we'll talk about the problem child, which is the B Victorias. So again, this is a megatree produced by Cambridge. This shows you all the sequences available through GISAID, and each one of those little lines on there, the black lines or the coloured lines, represent a single influenza B virus. And then on the bar chart there, you can see that there's viruses from around the world shown in different colours there, and you can see things have trended over time. So a few years ago, back in 2019, 2020, we had the B Washington-like viruses circulating. You see they're completely died off now. They had a couple of amino acid changes. We've got an update here with the B Austria, which has 3 amino acid deletions out of the HA, and they're the predominant virus now. And you can see on the right-hand side, we've got nomenclature for the Bs like we have for all the other influenza viruses. And the two main groups are the 3A1s and the 3A2s. And if you've got very good eyesight, you'll be able to see that the 3A1s have virtually died out, and we now have the 3A2 viruses circulating globally. Courtesy of NextStrain and their nomenclature system, we've even divided up the 3A2s into multiple subclades. As you can see, the nomenclature there for the subclades of the 3A2, and they've got a C nomenclature to them. And the majority of the viruses we've seen are in the C5 group in various parts of the world. For example, in the bottom of the little table there, you can see the C5.1s, which have been mainly found in North America. Here's another megatree just to show we can do sequencing in Melbourne as well. So these are viruses we've sequenced over this period of time, and shows you quite a distribution there over the period there. Different color codings for different months, but that's not the point I wanted to show. In the blue square there is a heat map of the reactivity using the B Austria ferret antiserum, both cell and egg. So this is a heat map. So gray is no reductions or less than 2-fold reductions, and red is 4-fold or 8-fold reductions. And if you scan down that, so through the entire phylogenetic tree there, they're all 3A2 viruses, no 3A1 viruses, and they're all very well covered by these 2 ferret antisera. There is a couple of red dots on there, but they're not in this period. So complete wipeout in terms of low reactors. And if we look at the diversity, so this is some data produced by CDC from the available sequence data from one period to the next, and you can see things haven't changed that much, but there has been an increase in this subclade of the C5.7s over this period of time. If you like to follow things in these sorts of frequency plots, you can see there is a little bit of variation from region to region, such as the North America showing the 5.1s, but the rest of the world more or less switching over to the C5.7s. And if you don't like those plots, then here's some pies for you, and shows you that most of Europe, Asia, Oceania have 5.7s, but there are other subclades persisting in South America, North America, and parts of Africa. So a number of those viruses are sent into the centres, and this is just showing you how many viruses we've actually looked at. So the CNIC in Beijing gets the gold medal for analysing most viruses during this period, with the others having fewer viruses to analyse. In terms of reactivity with ferret antisera, so these are post-infection ferret antisera against the Austria, which is the reference and vaccine virus, against the cell or the egg. It's virtually no viruses in most of the centres and a few in the CNIC. So this is about as good as it ever gets. If you need proof on here, here's a HI from the CDC, and the central columns there, which are marked in black, are the ferret antisera to the Austria cell and egg. And you can see there that there's no reductions or no significant reductions against either of the homologous titers there for cell and egg. This is a heat map, so if there was something bad, it would be in red. Everything to the right of those first two, which are the older viruses, are in yellow, showing little or no reductions. So Nicola's already explained the antigenic cartography map, so I don't need to go into this very much. So you can see here, this is data from the Beijing CC, and you can see here this egg in the middle, the B Austria, is surrounded by viruses in both panels here. What we have seen is a shift from this 3A1 shown in that dark green plot here in the bottom of the left-hand graph here. You can see that there were viruses circulating in China with this 3A1 phenotype. They've all gone virtually, and virtually none have been detected in this current period from February. And virtually all of those have moved into the top quadrant there. And virtually everything they've seen in the Chinese plots are from the C5.7 subclade. If you look at other centres here, so Beijing's in the top right there, but viruses analysed in the US at the Atlanta Centre, the Tokyo and our centre, you can see that the coverage is very close to that reference virus of the B Austria, with no other viruses detected in this period. So here is the serum panels that we've tested. These are the human post-infection sera that we obtained. And there was one panel from Peru, and the rest of the panels were from Australia. And as Becky mentioned, we had a mixture of egg-based quadrivalent, cell quadrivalent, and adjuvanted egg-based vaccines. So quite a good range there. What we are lacking is a pediatric panel for the Southern Hemisphere, and we might talk about that later. So here is a non-inferiority plot here. So blue is good, red or orange is not so good, and red is really bad. You can see here it's just about a clean sweep when we test these human post-infection, post-vaccination, I should say, sera, when we test them against some of these 3A2 viruses that have been in circulation recently. There's very good coverage across virtually every virus that we've tested and across all the centres, and there's really only one showing any reductions in that whole group. So again, almost a complete perfect picture. So in terms of antivirals, pretty good as well. So we've tested 2,153 influenza B viruses. Only 6 showed evidence of reduced or highly reduced inhibition against the neuraminidase inhibitors. There's a list of the substitutions there if you're interested in that. And for the baloxavir resistance, we didn't see any evidence of baloxavir resistance out of 1,685 viruses tested by phenotypic or genetic analysis. So in summary, only B Victoria viruses circulated. After March 2020, we haven't detected any within the system. None have been confirmed, even if they've been reported on the FluNet system. They haven't been confirmed by any of the collaborating centres. We've got a very clean sweep there in terms of the phylogenetics or genetic analysis, where all of B viruses are in the 3A2 clade currently, which is good news. We have some subclade variation, but they're quite minor. If you look at the phylogenetic trees, there's either single amino acid changes or no amino acid changes between some of these subclades. In terms of their antigenic characteristics, again, they're very homogeneous and they're very well covered by the B Austria, like ferret antisera, either cell or egg. In terms of human serology, again, we have very good coverage using the Southern Hemisphere 2024 post-vaccination sera, and they all cover, those sera cover all the 3A2 viruses which are currently in circulation in the Southern or Northern Hemisphere. So the B story is very good.
I do think we'll have a chance to introduce Todd David from WHOCC. Todd.
And Ching, I may need your help here as well. Thanks. While Wenching's helping out. Great. And perfect. Thank you. All right. Thanks, everyone. Great to be here this morning. Thanks to the organizers for putting together such a nice meeting for us this morning. I'm Todd Davis at the Center for Disease Control and Prevention in Atlanta. And I lead our zoonotic virus activity as part of our WHO collaborating center. And I'll be talking about zoonotic infections and animal virus activity over this reporting period with help from quite a few collaborators, as well as our OFLU group that represent animal laboratories around the world, including representatives from the World Organization for Animal Health and the FAO. So I'll start with just a brief snapshot of what this reporting period has looked like relative to previous reporting periods. As you can see, on the far right-hand side of this slide, the number of subtypes that have been detected really has not changed from what we've seen over previous years. So we haven't seen any major spikes in the number of zoonotic infections in this reporting period. And as you can see, it's pretty typical of what we would expect to see over this 6-month reporting period, but with a number of different subtypes. And so all of those colored rectangles indicate different subtypes that have been detected. And I'll go through each of those subtypes in more detail so we can look at the genetic and antigenic diversity of those viruses, as well as the recommended candidate vaccine strains. So I'll start with a picture of the map of the distribution of where avian influenza viruses were detected in animals. As you can see, the majority of these viruses represent H5N1 subtype strains. There were a few H7s detected in the reporting period. We still have not seen any evidence of H7N9 over multiple reporting periods, but there were outbreaks in South Africa, for example, of highly pathogenic H7N6 viruses, and even a few sporadic outbreaks of high-path H7 here in Australia. But again, the majority of the viruses that have been reported are H5N1 strains, despite a few neuraminidase reassortments that continue to circulate in different parts of the world. The focus has been on H5N1. A lot of the viruses that have been detected in parts of Europe represent the 2344B viruses that we've been talking about now for several reporting periods. And those viruses still appear to be distributed quite broadly, primarily through movement by migratory birds. In the United States, of course, there has been a new host of these viruses identified in the US in dairy cattle. I know we've heard a lot about this. To date, there have now been 238 farms detected in the United States with positive H5N1 confirmed dairy herds across 14 states. With the most recent state being California, that has a large number of dairy cattle herds in the United States. So we're monitoring that situation very closely in the US. The other thing I'll just add is that, as we've been monitoring these viruses for their distribution, we're also occasionally finding other mammals that are infected. So last reporting period, we were talking a lot about sea lions, other marine mammals, and there do continue to be sporadic detections in those other mammals as well. But in terms of the human infections, there were 26 Goose Guangdong lineage H5 human infections detected in the reporting period. There were 6 in Cambodia that belonged to the clade 2321C group of viruses, 1 in Vietnam. In the United States, there have been 14 cases detected associated with exposure to dairy cattle or poultry, and one person in Missouri that was not able to identify exposure to animals. So we're again closely monitoring those exposures in individuals that are working with dairy cattle and poultry as well. Those have been mild cases in the US, with primarily people presenting with conjunctivitis as a symptom of infection. In China, there's also been a couple of fatal cases. So there was a fatal case of 2344B, 2 fatal cases of 2344H, which is a clade of viruses that still does continue to circulate in China. So watching those quite closely. There was one case reported in Australia, the first H5N1 case reported in Australia, but this was an individual that had traveled to India and was diagnosed after returning home. There was also a traveler-associated case reported in China of an individual from Vietnam. And then finally, one interesting case, the first ever human case of a low-path H5N2 virus detected in Mexico. And this is a non-Goose Guangdong lineage H5 virus. These are strains that circulate endemically in poultry populations in Mexico. But this person did have severe underlying medical conditions that likely led to the fatal outcome. So to turn our attention to the clade 2321C viruses, again, these are viruses that have historically circulated in the Mekong Delta region of Southeast Asia. These viruses still circulate in poultry populations in Vietnam, Laos, and Cambodia. And there have been, again, a number of human cases associated with poultry exposure to these viruses in Cambodia and Vietnam, some of which have been fatal. As you can see from the phylogenetic tree on the right, these viruses continue to diversify and have genetically diversified away from the candidate vaccine virus, the duck Vietnam 1584-2012 CVV. So it's been more than 10 years since we've had to recommend a new virus to cover the 2321C viruses. But based on antigenic data performed by St. Jude Children's Research Hospital, as well as at the Francis Crick Institute and CDC, we do see that these viruses do have reduced cross-reactivity to the duck Vietnam 1584 ferret antisera. So really, for the first time in this reporting period, we've started to see consistent reductions in viruses that represent the 2321Cs from Cambodia and Vietnam, with greater than 8-fold reduction in these titers in some cases. So we have decided, after looking at quite a lot of data, to make a recommendation to develop a new clade 2321C candidate vaccine strain that represents a Cambodia 2024-like virus. The 2344Bs, as I mentioned, remain the primary subtype that's been detected in birds and also in mammals that have resulted in the larger number of human cases. The phylogenetic tree on the right-hand side shows the genetic distribution of these viruses, and the viruses that have been detected across parts of Asia and Europe, while they have genetically diversified, are still relatively well covered by at least one of the clade 2344B candidate vaccine strains. And then in the top portion of the phylogenetic tree, you'll see the clade and the subclade that represents those viruses that have been detected in dairy cattle and also in poultry outbreaks associated with those dairy cattle viruses, as well as the human cases that were detected in a couple of different US states. And what we find is that looking at the sequence data, a lot of this coming from the US Department of Agriculture, is that there are limited changes occurring, especially in the hemagglutinin gene of these viruses. So there tends to be genetic stasis among the viruses that have been reported in dairy cattle. So we monitor this very closely. We've continued to do antigenic characterization of these viruses. This is one example of an HI test performed at CDC, where we looked at human cases from Colorado and Michigan and compared those viruses to ferret antisera that's been raised to the available 2344B CVVs. So the A astracan CVV is RG71A. As you can see, that ferret antisera does cover these viruses well, within 2-fold reduced titers for the majority of viruses tested. RG78A is the American Widgeon South Carolina virus. This one also covers these viruses well. And then finally, RG80A, this is a chicken Ghana CVV that also covers these viruses quite well. So among those candidate vaccine viruses, for now, they are covering these viruses very well. We have seen a couple of sporadic viruses detected in dairy cattle over the past several months that have sporadic mutations in the HA that do result in reduced cross-reactivity to the RG71A as well as the RG78A CBV. Those represent a few changes that result in a gain of glycosylation or changes in antigenic sites that we know impact cross-reactivity. But the antigen to the RG80A and that ferret antisera does cover those viruses well. So again, monitoring the situation very closely, but based on the currently available antigenic data, we are not recommending a new 2344B CVV at this time. On to H9N2s and H10N3s. There have also been a number of H9N2 human infections. The majority of those have been reported from China, ranging in individuals that had mild to severe disease after exposure to poultry. There were also cases reported in Ghana, in India, Vietnam, Hong Kong SAR, and then finally an H10N3 virus that was detected in a severe case in China, which I'll talk about in more detail. The H9N2 viruses remain antigenically well covered by the available candidate vaccine viruses, so we will not be recommending a new H9N2 CVV for this reporting period. The H10 viruses, interestingly, have continued to be detected, albeit sporadically after exposure to poultry that harbor these H10 viruses. There's a number of different neuraminidase that have been detected. The primary neuraminidase have been N8s and N3s. This particular case was an H10N3 virus from Jiangsu province, from Yunnan province. Unfortunately, the virus couldn't be isolated from that clinical specimen. And so we did look carefully at previous detected cases and virus isolates that were available from those cases. And we do have a genetically related H10N3 from Jiangsu province from 2021. And CDC has begun to do some preliminary CVV production against this H10N3 virus. These viruses are also quite interesting in that they've accumulated the internal genes from H9N2 viruses. And based on the sequence data provided by China CDC in the human case from Yunnan, we noted that there was also an increased proportion of alpha 2,6 mutations that would likely give this virus the ability to have dual receptor specificity with the change of position 226 to a leucine. And then the polymerase genes also have a number of markers that indicate the possibility of mammalian adaptation in these strains as well. So based on that data, we have decided to recommend an H10N3 CVV to the Jiangsu 428-2021 virus. Moving on then to swine influenza virus detections and the H1 variant viruses. Again, this is a map that's provided by our OFLU colleagues. Looking at the genetic distribution of these viruses around the world. As you can see, looking at North America, both in Canada and the US, there's a number of different clades that remain circulating in those swine populations. Europe as well, you can see based on just the wheels that it's quite a lot of genetic diversity among those viruses that represent all of the H1 clades that are detected in pigs. Russia also shared some data to indicate genetic diversity among viruses in pigs and those populations as well. For the human infections in the United States, we detected 5 cases for the reporting period. One of those was an H1N1 variant. The other 4 were H1N2 variants, but all belong to the 1A.1.3 group of viruses. This is a lineage that we previously referred to as the alpha lineage strains, of which we've developed numerous CVVs over the years. These were all individuals that were exposed by attending agricultural fairs or swine exhibitions in the US. And then there was one fatal case identified in Vietnam of an H1N1 variant belonging to the 1C.2.3s or the Eurasian avian-like swine viruses that have been detected for many years. This person did have underlying medical conditions, which again were likely to lead to the fatal outcome of that infection. So looking closely now at the 1A.1.3s or the alpha lineage viruses, you can see those human cases that were detected in the United States, primarily from Pennsylvania and one case from Ohio. There is some genetic diversity among those viruses, especially related to the closest CVV that was recommended against the 2021 strain. And based on the antigenic data that we analyzed at CDC, we did note that among the ferret antisera raised to those candidate vaccine viruses representing the 1A.1.3 group, that we saw significant reductions in cross-reactivity against these more recent viruses. So quite significant reductions where we saw nearly no cross-reactivity against the previously recommended and developed alpha lineage CVVs. We did generate ferret antisera against one of the Pennsylvania wild-type viruses and demonstrated that that ferret antisera did cover the other human cases that were identified in the reporting period. So based on this data, we are recommending another 1A.1.1.3 CVV called A Pennsylvania 27/2024. And then finally, the H3N2 swine viruses also remain in circulation. Interestingly, quite a lot of data in the US, not much in other countries, likely representing just some gaps in surveillance, and being able to detect those viruses in other regions. But in the United States and Canada, we do see, again, quite a lot of genetic diversity among the H3 viruses and a strain that was detected in Kazakhstan. For the human infections, there was one case of an H3N2 strain that represents the 1990.4A group of viruses. And in the US, also another one representing the 2010.1 strain. These were mild cases, as is typical of swine influenza infections in humans after exposure to pigs. And then one case also reported in Canada. The antigenic data, which I won't show, did tell us that these viruses are well covered by the existing candidate vaccine strains, so there are no recommendations for H3N2 variant CVVs. And with that, I'll close out. And thank you.
Okay, so now we are in the conclusion part of the presentation. I would still like to take one step back to first acknowledge the foundation of this work. This is a global influenza surveillance and response system, already mentioned by a couple speakers in this meeting. And just to say that currently this network comprises 152 national influenza centers in 130 member states of WHO. GISRIS is being acknowledged increasingly its special value. And this is all because of the efforts by generations of people in the network and its hosting countries. But it also includes all of you, GISRIS partners, including everybody sitting in this room here. Start from Monday this week, WHO conveyed a consultation from 23 to 26 from Monday to Thursday to review, to analyze, and to do the conclusion of recommendations that I'm going to announce. This was an in-person meeting and was chaired by Professor Ian Barr. 10 advisors attended the meeting. They are all directors or deputy directors of WHO CCs and WHO Essential Regulatory Laboratories. At the start of the meeting, interest declared by these advisors were disclosed to all meeting participants. In addition, 45 participants observed the WHO consultation. These observers were from the GISRIS network and its partners, including veterinary sector. In addition, we also have colleagues from WHO regional offices and country office, as well as HQ, attended the meeting. And actually, as already mentioned by Ziping in his opening remarks, that massive volume of data was reviewed in the consultation, and this is a list of the category of the data. And from the presentations of the advisors, we could already get a glimpse into the volume of the data. I would like to say that in the recent years, there's been more and more data available for the deliberation and providing stronger evidence base for the WHO's recommendation. And the conclusion or the recommendation is always made by the WHO temporary advisors. So this is a conclusion based on the intensive work of the surveillance as well as the consultation just passed. It is recommended that for trivalent vaccines, for use in the Southern Hemisphere 2025 influenza season contains the following. For egg-based is an A Victoria 2022-like virus, and Croatia 10136RV23-like virus, and A B Austria 2021 Victoria lineage-like virus. For cell culture-based, recombinant protein-based, or nucleic acid-based vaccines, and A Wisconsin 67 2022-like virus, and A District of Columbia 2723-like virus, and B Austria 2021 Victoria lineage-like virus. And of course, from this recommendation, we can see that there is an update on the H3N2 component, an update from the Southern Hemisphere 2024 recommendation, as well as an update from the Northern Hemisphere 2024-2025 recommendation. Now on the quadrivalent vaccines. So consistent with the previous WHO recommendations made in September 2023 and February 2024, it remains the opinion of the WHO's Influenza Vaccine Composition Advisory Committee that the inclusion of a B Yamagata lineage antigen is no longer warranted. So every effort should be made to exclude this component as soon as possible. National or regional authorities should make decisions regarding the transition to trivalent vaccines in their jurisdictions. So where quadrivalent vaccines are still used, the fourth component is recommended, that is B Yamagata lineage virus, a B Phuket 2013 like virus. So to support the vaccine, a new round of vaccine cycle, the candidate vaccine viruses and reagents are available on that website with the link provided here. I would like also to mention that twice a year, in addition to the seasonal influenza vaccine composition recommendation, the WHO collaborating centers, EILs, and experts in the consultation also reviewed thoroughly the data available on the zoonotic influenza, as already presented by Todd this time. So a summary report of zoonotic influenza characterization and candidate vaccine viruses for avian and swine influenza, including avian influenza H5N1, are also available on the WHO's website with the link indicated here. And we expect that those websites could go live like around noon today. In addition, in view of the increasing needs for communication, FAQ also has been published accompanying the products delivered from this consultation, and again with a link here. For countries in the tropical and subtropical regions, there will be a need to decide which formulation, i.e. Northern Hemisphere recommendation or Southern Hemisphere recommendation to follow. So for this, we also, WHO has a guidance document published with the link indicated here. So let me just stop here and pass over to the next presenter.
Okay, good morning, everyone. I will provide a brief update on the candidate vaccine viruses and potency testing reagents that are required to implement the recommendation that you just heard from Wenjing. And I promise I won't keep you from tea and coffee for too long. So first to the candidate vaccine viruses. For H1N1, there has been no strain change, so you're all familiar with the CVV, so I'm not going to read through the table. You will have, or many of you will have already experience with one or more of these CVVs, and they're of course listed on the WHO website. There are lots of CVVs available for egg-based vaccines, and there are also CVVs, both wild-type and reassortants, available for cell culture-based vaccines. And if you're producing recombinant protein vaccines, then the sequence of the HA antigen should match closely the sequence that is listed here with the accession number from GIS8. Now for H3N2, there has been a strain change. As you just heard, the recommended prototype is A Croatia 10136RV 2023. And I'd just like to point out a minor thing, which the eagle-eyed among you may have noticed. You will have seen the name of this strain before, but it contained a slash between the 6 and the R. This does not fit standard nomenclature for influenza, so we have decided to change this. And this should also have been changed or will be changed shortly on GIS8. So please note that if you search for this virus now, the slash is gone. Now, there are two reassortants available for that have been derived from Croatia, 10136RV, which have passed the two-way test. And those are listed here, NIP 146 and New York Medical College X425A. The wild-type District of Columbia 27-2023 virus has also passed the two-way test against Croatia, so is a like virus. And more CVVs are in development and are close to being tested, such as reassortants derived from District of Columbia 27. And these viruses will be available from the labs such as MHRA, New York Medical College, and others shortly. There's also a CVV available for cell culture-derived vaccines, and that's a virus District of Columbia 27 isolated on a qualified cell line. And that's available from the CDC in the United States. For the B Victoria lineage, this virus has been in the vaccine for a while, and so you will be familiar with the CVVs, and I don't think I need to read through the list. Similarly, for the cell culture-based vaccines and the B Victoria lineage, there are two CVVs available. There probably won't be much use for B Yamagata lineage CVVs, but if you do need some CVVs, then they are listed here, and there's quite an array available. And there are also CVVs available for cell culture-based vaccines for the B Yamagata lineage. Now to the potency testing reagents. Again, no surprises for H1N1. All of the ERLs have generated egg-based reagents for IVR 238, as well as matching anti-sera. For cell culture-based vaccines, there are antigen reagents available for the CVR 167 cell-based antigen, as well as for a recombinant HA vaccine based on West Virginia 30 and the matching anti-sera. For H3N2, obviously, since it's a new strain, reagents aren't yet available, but will be made available by the ERLs. And I encourage everybody to attend the technical teleconferences that will be started again soon, where updates will be provided. For the B Victoria lineage, antigen reagents available for both a wild-type virus, Michigan 1, and for the reassortant DVR26 from the ERLs, as well as the matching antisera. And for cell culture-derived vaccines, again, antigen and antiserum reagents are available. And finally, for B Yamagata lineage, reagents are also available from the ERLs for both egg and cell-derived vaccines. And just to remind you, Wenqing already showed these updates are available on the WHO website. And with that, I'll hand back to the chair. Thank you.
Thank you very much for the presenters. We have very good timing. So we have 25 minutes take a break. I know people wanted to talk to each other, so and take a biological break too. So we back on 11 at 11 o'clock because we want to finish at 12 because people have a flight to catch. All right, I'm back on 11. Enjoy your time.